Chapter 12, torsion in circular sections, and what more to say? Let's just get started. So it's a twisting action that's caused by a couple or a twisting moment, and it's applied in a plane perpendicular to the longitudinal axis, and that's something that's called torque. Okay, so torque is being applied to this. How come you can't see my mouse, can you? I see it ain't writing. Let's see if you can see my pen. Yeah, okay, you can see that. But the torque is applied here and here. If we're applying it here and here, that's creating a couple, right? Equal and opposite. Okay, so that's known as torque, and that's an external torque that's applied. Now what we're going to be talking about will be internal torque that will resist that. So that's basically what we're trying to figure out. If you've got an external force applied to it, what's it going to take for the material that you're using to resist that external force? Okay, which is nothing any different than what we've been doing up to this point, is it? Worst part about it, I can't hardly see that on my screen. But so we've got some different situations that are occurring here, and you can, if you're following along in the book, maybe that's about my best bet as far as being able to see it. We've got two situations that are occurring here. Okay, you've got, well, in that particular example, basically only shows one, doesn't it? Okay, well, you've got two different situations that are occurring here. You've got, well, let me back up a second. You've got those two states to consider, but you also have to consider that these members are in static equilibrium. In other words, nothing is moving here, right? Which is kind of where we've been the whole semester. But you've got the situations where the subject are subjected to twisting actions caused by either a pair of externally applied couples acting in parallel planes, okay, which you will see in the next slide, which is using pulleys, okay, or a single external couple applied to a member that's fixed on one end, which is what you're seeing in this example. I guess really equal and opposite, they're showing it in this top left example. You are seeing that. Let me get my pen here instead of the highlighter. But they're not showing the actual pulleys. So when you go to the next slide, you'll see this situation is occurring here. This is the two equal and opposite, or the couples. Okay, and then in the top portion here, now what they're showing you here is this free body diagram is where they're cutting through somewhere in this section right here. Oops, somewhere in here they're cutting through, and that's where you're looking at that section. So you're when we consider the torque or the torsion in these mechanisms, if you will, we're going to be looking at some area, if you will, inside the two couples. You can cut it anywhere in between there, and it's going to be pretty much the same no matter where you're at within those two external forces, if you will. There's some kind of torque that's being resisted within those two planes. Okay. Same thing is occurring on this second one here, but the wall is resisting as opposed to a cup, or as opposed to one of the pulleys. So it is actually creating an internal torque in that helps resist it. So something has to hold it back for that thing to have torque, right? If they're internal torque. If it's freely spinning, nothing, if you just, in theory, it would just keep spinning forever, right? There's no torque involved. It's not, there's nothing trying to make that thing twist apart, if you will, if there's no resistance. But as soon as you put resistance, in other words, and they could actually be going in the same direction, but there's something out on the end of that chain, if you will, on that pulley that is having to be driven. You've got a motor driving this whole shaft, and then that shaft transfers energy to another shaft that's turning a wheel, let's say, on your lawnmower. My old lawnmower was like that. It had drive motors, and they had a sprocket on them, and there was a chain down to the wheel. Well, there's still torque applied in that shaft in there, in both of those shafts. But they're still turning in the same direction. But there's resistance from the ground making that tire want to resist, if you will. Okay, between the ground and the gravity, there's resistance there. Now, if all of a sudden I break traction, if I'm in a dragster now, a dragster lawnmower, torque goes away, doesn't it? Shaft, there's nothing to resist that. But as soon as it bites again, torque is back involved. And they were still going the same direction. Both shafts were going the same direction. So don't think that that it can't be moving per se. You can still not have torque. They both are still moving, and they can both be moving in the same direction. But there's still some kind of external force being applied to that system to make it drag down, if you will. Okay? So keep that in mind too. Now, in the case of the wall there, no, sorry, it's not moving. If it's moving, it's deforming, isn't it? So there's always going to be I guess there'll always be some kind of torque there as long as you've got something trying to twist it. If there's nothing trying to twist it, of course, there wouldn't be any.
What did you mean when you said if you went to from your regular mower to a dragster, then?
Well, if you broke traction. I broke traction, and now I'm just smoking the tires right to.
Okay, so there's nothing resisting you.
Exactly. Yeah. That was just a maybe a fun example, Although I guess even at the drag strip when they pour down their liquid and smoke the tires, there's still resistance in there. If there wasn't, you wouldn't have any smoke. So there is still resistance, so there is some torque still applied. But if you were sitting on ice, it wouldn't be, maybe. Wouldn't be any, would there? That's the worst thing for an old guy. Ice.
Isn't that how?
Break a hip.
Isn't that how like the perpetual moment clock works? Like they're trying to remove all the torque and tension in there.
And friction, yeah. So, which I guess it was Tesla. He was one of the only ones that ever basically came up with that, and then they shut him down. So let's see what else here on that particular slide. It's easier for me to read this one. Yeah, we talked about all that. Now, I think that's the last slide I actually have any real knowledge, if you will, imparted any knowledge there. But let's see. Now, we've got case of two equal externally applied couples acting in opposite directions on parallel planes, and that's basically what we've got going on in this example. Okay, so we've got this shaft. Now, somewhere in there, does it say, yeah, here's the driver pulley. Okay, when you've got a shaft situation, you've got to have a driver pulley. In other words, this one is getting all of the torque supplied to it via some kind of a V-belt, a chain, or it could even be another pulley, couldn't it, in contact with it. I've seen rubber pulleys where they have rubber around the outside, and they just contact each other, and so a motor is probably supplying some kind of an external force to this of 2,400 pounds inches, excuse me. Then you've got these other pulleys. Now they're going in different directions. Okay, so you're going to have some kind of torque buildup in that shaft, aren't you? Let's see, and it is parallel planes. All these pulleys are on parallel planes. What else about that? Let's see. I guess we talked. Well, the magnet. Note that, and let's back up here one. We should still be talking about this. In Figure 12, let's see, 12.2b. What they said, basically what we said there was this bar is cut in half, and you're only looking at one side of it. Okay, and what you can say about that, the magnitude of the torque in that bar is equal to one of the two couples, and that is denoted as the force D. Okay, and do they have that? Did they show that there? Yeah. Over here they say the torque is equal to FB, and it's just the force times the distance of one of those couples. Okay? So the force times the distance of just one of the two couples. So when you cut it in half, you're taking care of that, aren't you? Okay? So I guess what would the other one would, and I think I did allude to this, the other pulley acts like the wall, doesn't it? Because the torque in that bottom shaft is the same thing. It's the force times the distance, or just the moment, right? So, does that make sense? That the torque would be the force times the distance, or the moment? Think about a torque wrench, or any kind of a wrench. What are you developing? You're developing that moment, which is a force times the distance. Okay? A little bit different there, but it's
So that distance is not to the axis, but all the way between the two arms of the force, or the two forces.
right. That's how a couple works, right? It's one of the forces times the distance between those two. So in other words, if that's the steering wheel, remember I think we talked about that way back when. If it's the steering wheel, it's the distance between your hands on that steering wheel, if you will, and then whatever one hand is supplying. But for them to be supplying, they both have to be supplying the same amount, right? But you don't take two times that force; you just take one. So, excuse me. That's how a couple works. One force times the distance between the two. Or you could even look at that as the diameter, especially when we're dealing with pulleys. Think of that D as a diameter. Might be an easy way to remember it. Okay, so let's see what else about that now. Figure 12, that was 12.2b. 12.2c, the bar is rigidly fixed. There's no rotation. The equilibrium exists due to the equal and opposite internal torque. So again, that's at force times the distance. Note, torque is expressed in units of pounds inches or pounds feet. Okay, you might see pounds feet. They don't talk about pounds feet in here, but on my motorcycle, I'm dealing with pounds feet and pounds inches all the time, depending on what size bolt you're trying to tighten up. You know, the smaller machine screws, you're dealing with pounds inches. When you're dealing with an axle bolt, you're dealing with pounds feet. So that's kind of a little bit of what they say in the book is pounds inches, and they make it sound like that's the only thing you're ever going to deal with. That's not the case. But they do say pounds inches, pounds feet, Newton meters, Newton millimeters maybe. I don't know. I guess that would be the case. But they do. It's not foot pounds. Like you always hear, people will talk about foot pounds. It's pounds feet. All right, Howard?
Distance between two forces should be perpendicular, or maybe any distance?
They have to be perpendicular forces, right? So if you've got some force that's not perpendicular, then you're going to have to break it out and figure out how much is applied to that torque. Is that what you're saying?
The distance D is the perpendicular distance between.
That's correct. Perpendicular to the forces, yes. Is that what you mean?
Showing that inclined distance.
Do what?
They are showing in figure inclined distance is not straight. The D is making angle.
That's all because the.
Well, that's just because it's an isometric view. That would be no different than if we looked at the end of that shaft, the end of this shaft right here. If we looked at the end of that, there's your circular shaft, and there's one force going down this way and one force going up this way. And then the diameter is right here. Okay, so that's D, and this is the force, and that's the force. So it's the force times the distance. Does that help?
Yes, a lot.
Okay. I'm sorry, I didn't understand exactly where we were headed on that. That's why you have to keep going with me here. Sometimes I'm not quite clear on that. Okay? So, expressed in pounds, inches, pounds, feet, Newton meters. Okay?
If we were converting pound inches to pound feet, times 12.
Yep.
Divide.
Or it's either divide or let's see if it's let's see if you're doing, you've got, now that is, keep in mind that is pounds times inches, right? That's what that little dot in there, it's pounds inches or pounds feet. If you were going to multiply that by what, you'd have 12 inches in 1 foot, so you'd be dividing it. Bless you. Okay? So, yeah. And you'd still be, then you'd be at pounds, feet. Now, nice thing about it is you get the right torque wrench, it's all done for you, right? Get one that's digital. Takes care of that. It does Newton meters and all that too, a lot of them. So it's kind of handy.
The ones that scale it for you. Using that. The torque wrench.
As far as, what do you mean by scaling it?
When you put it on there, it'll start dialing up, and that's the digital. It'll dial up until where it is, and it'll kick back down to where it needs to go, and then turn on.
I don't guess, I don't know if I'm following you on that one.
You dial up the digital one. Put
Yeah.
It in there. This one, it doesn't, it calculates it all for you. Just put it on there and pull the trigger, and it does the math. All the gears inside.
Oh, on mine, you just push a button to change the units, and then push it to where you want to go to, and
This one that I saw, so the neighbor has it.
that must be a new fandangled one. Yeah, makes a difference.
Like an expensive torque wrench. So you don't actually wrench on it, so you just put it on there and push a button?
I just get rent the whole.
He doesn't have to actually pull?
It's kind of like an impact wrench.
Okay, now I'm with you. Because it's like, wait a minute, I mean, I set mine and you pull it and it'll start showing you the numbers of torque.
Right.
And when it gets to that value, it shakes, it vibrates and sends off a
Yeah,
light.
Think of the impact wrench style.
Yeah, that's, I've never seen one of those. Okay, so what else about this? Let's see. I guess we need to do that example problem there on, oh, and I did talk about the driver pulley, right? On this, we talked about one is a driver, that's what's going to be supplying the external force, and then the other pulleys will help resist that, so you do have an internal torque going on there. Okay? So the driver, I'm trying to find my mouse. This is the driver, and these would be driven, or what the book calls here is, sometimes they say they're power takeoff pulleys, but I think a lot of times you're going to hear that as the driver and the driven pulleys. Okay? That's what I've always heard it referred to. But it is a power takeoff, isn't it? You're taking power away from that shaft and putting it on something else and making it do something, no matter what it might be. So somewhere down the road, this is, you'll be doing a shaft design problem similar to this in machine design. That is, if you're, I'm assuming you guys are all going to take that. I don't know. So, example problem 12.1 now. Let's see. And this is the right picture, I guess, for that. Calculate the internal torque at sections RR and SS for the shaft shown in this picture we've got here, 12.3. The shaft is acted upon by the four torques indicated, assuming negligible bearing friction. In other words, we're not going to account for any friction based on those two bearings that are holding this shaft together, okay? Which there shouldn't be that much friction anyway. So the solution, note that pulley B is the driver. The other pulleys are power takeoff. So the torque of the 2,400 pounds-inches at B is balanced by the three torques of 600, 1,000, and 800 at A, C, and D respectively, which are in the opposite direction. So, in other words, that thing's in equilibrium, right? Because of those, and they're going the opposite direction. So, you know, if you total those up, they equal 2,400. All right? So therefore, the entire system may be thought of being steady-state equilibrium. It's neither gaining nor losing speed. If the system as a whole is in equilibrium, every segment of the system must also be in equilibrium. True. To determine the torque at section RR, cut section RR perpendicular to the longitudinal axis of the shaft, anywhere between pulley A and B. So we're going to take, in theory, we're going to take a saw, right, and cut that. Well, they're showing it right here, aren't they? RR. Anywhere between A and B. So that's what they're doing here. Okay, and consider the left portion of the free body diagram, or the free body is shown in the next little bit here. So we go to that one, and there's the cut. So, for equilibrium, the summation of the torques must equal 0. And they show that in the book as the summation of the torque equals 0. This is the same as saying that the external applied torque must be balanced by the internal resisting torque that is numerically equal but opposite in direction. So what would the torque in that section be? Just based on that. Not a trick question here now.
600?
600. Going the opposite direction. So if it's 600 pounds-inches, right, going, I don't know how we want to say that, counterclockwise if we're looking at it from left to right, then the torque that's going to be in this shaft right here is going to be 600 pounds-inches going the opposite direction. That's all they're saying there. Okay, now, seems easy, right? What we're probably going to be charged with is figuring out what that 600 pounds is, 600 pounds-inches is on that pulley A. That's what we'll end up having to figure out so that we can figure out what that torque is in that, or that torsion that's, you know, going on in the shaft. But probably more importantly is we're going to have to figure out what the stresses are that are involved there so that we can make sure, and it's going to be shear stress in that. Okay? But it's torsional shear. If you twist something hard enough, you can twist it in two, can't you? In fact, well, a bolt that's locked up, you know, that's rusted, you know, you keep twisting, and sooner or later that thing just spins apart. That's torsional shear. Another case of that, what else? What else could we say? Where else does that happen?
A piece of wire.
Yeah, but that's more of a fatigue type thing, I think, going on there. You know, you'd have to, depending on how ductile the wire is, especially, you know, then you start getting into some other material sciences, like holy cow. So, but the bolt is about the best one I can think of right off the top of my head. You know, if if you've got a bolt that's rusted up, a bolt in the nut, and when you start, oh, and you can even do that. Of course, you can do that to anything that's not rusted too, can't you? If you've got some kind of a, well, let's just say if the hinge on my glasses, you know, if you tighten that too tight, it will pop off and you're screwed.
I
So,
don't understand why they make drain plugs for boats out of brass. I snapped like 3 drain plugs on my boat.
well, it probably has something to do with thrust, would be my guess.
Stainless steel, it works.
Yeah,
Rusty, but it's a soft metal.
and that,
Some drunk idiot gets behind the boat and tightens it too tight, and then I gotta go and get it off.
yeah,
And it breaks.
Problem with steel and aluminum though is your negative battery terminal is going into your chassis on your boat. You get corrosion.
yeah, oxidation, or not yeah, it is kind of an oxidizing,
Yeah.
yeah. Any rust is an oxidation process, isn't it? So, yeah, that I don't know that much about it, but
I don't
that's,
either, but it's frustrating.
yeah. But, and even at that though, it's a softer material. Maybe it's easier to deform to
Seal.
seal that up. I don't know, because that really the rubber around there, isn't it?
No,
There's no rubber involved.
brass to brass. Like
Oh, okay.
inlet brass, and then
Well, I guess that's how it does tighten up too much and
yeah.
shear it off. Oh yeah, and you don't want that to happen at all. Or sheet metal screws. Sometimes you're putting a sheet metal screw in and you're putting it in a thick piece of material that you can't overcome those threads, and the threads don't just pull out. Then you're going to spin that head of that screw off, and you just did a torque type application where you did a torsional shear. Is what's going
But
on.
deck screws in happen a lot too.
Yeah, same thing. So, yep. So that's where we're at on that. Now let's see what else about this. Okay, so we figured out that that's 600 pounds inches. Again, that's what has to resist between pulley A and pulley B there. That's all you have built up in that. Okay. Well, now what happens? Let's see. Using the same approach, calculate the torque in section S. Well, section S was this situation. We went farther down the shaft. So what do you think might have to happen there? You have to do a summation of those torques, don't you? So as we progress at different places on that shaft, we're going to have different torque ratings, aren't we? So what would you think then in your machine design class, what would you do? You'd ask the instructor, what do I do, right? I know how you guys are now. It's just a different world now. What you would do is you would have different diameters on that shaft, wouldn't you? It wouldn't all have to be the same diameter. Now, if you wanted to over-engineer it, I guess it would be. But how we'll make it all one, that kind of sucks, Or maybe you don't have, the pulleys aren't set up like that you're trying to buy. They'll have different diameters, so you have to make sure that the internal diameter on a pulley that you wanted to slide onto a shaft, would still allow you to create a shaft big enough for that.
Varying speeds.
Do what?
You need different speeds coming off.
As coming off the pulley, well, and typically they are, because the diameter of the pulley is going to have different speeds coming off. So, but down at the axis though, what's the speed
Of the driver of the power takeoff.
of any of them? Down at the axis of that shaft, the speed is 0. Just like the torque is going to be 0. We'll talk about that here in a minute.
Based on the diameter.
And it goes right back to the diameter of the pulley. That's why they have different speeds, and you'd have different torque values, couldn't you, coming off of that? Different F times D, if you will. So that we're getting a little bit ahead right now, though. So note there on page 249, they do talk about the fact that you do have to sum those torques up. So the internal torque is equal to the external torque, and in this case Now, be careful, because you have to do this a little bit differently. It's note that you've got 2,400 inch-pounds going one direction and 600 pounds-inches, excuse me. I slipped right in there, didn't I? Going the opposite direction. So in this case, to sum those up, it would be 2,400 minus the 600. So what we can say then is between B and C, the torque that would be in that shaft would be 1,800 pounds-inches. Going which direction?
Same as the 600.
The same as the 600 that's showing here, right? Yeah. It's kind of hard to say. Clockwise, counterclockwise, it depends on which way you're looking at it, isn't it? If we're looking at it left, looking to the right, the torque in this shaft would have to be going, well, in this direction right here. Okay, where it says shaft, it's got that arrow pointing. That's the direction that the torque would be. The internal torque would have to be going, isn't it? To resist that. Does that make sense? Remember, the torque in the shaft has to resist the torque that's being applied externally. And if that's the case, this 2,400 is beating the 600 all to pieces. So there's 1,800 pounds-inches going this way externally. So internally, it has to go the opposite direction. Okay? Al, you're looking at me like you're not sure about that.
No, I'm thinking if we're looking at what's going on between B and C,
Oh, you're ahead of the game,
what
huh?
does A have to do with that?
What does what now?
Well, the, between B and C, you get the 2,400 and,
Well, what A has to do with that is A is helping that shaft resist that 2,400 pounds-inches. Isn't it?
yeah.
Well, sure it is. It's all one system, right? They're all keyed together, so they're all spinning. Okay? Again,
Yeah, I got confused because on the first section that we looked at, we're only looking at, what's going on in A and B.
Mhm.
And then we're looking at what's going on between B and C, but A is still involved. And I'm thinking like, well, there's other pulleys down on the end that you're not.
and let's go back to way back when we first started our class, and we did those sections of the when we were looking at members to try to figure out what was going on in those trusses, and we did the method of sections, and we cut that truss, and we looked at everything to one side. So what we did was we cut it, in this case, we cut it early on, and then we cut it again, and every time we cut it, we have to add all those forces that are acting on that new system. So we can't just ignore what's going on at A, because it is still something that's going on this, if you will, new little system that we're diagnosing. So you have to apply all the external forces to this system that are shown for the section we're looking at. Okay?
So section SS includes pulleys A and B.
That's correct. And if we were looking at it from the right side, if we cut it at that section, we would be looking at the pulleys C and D then. See, if we went all the way back to here, if instead of looking at the left side, we were looking at the right side, we would be dealing with C and D. The only problem is we don't have the input
Yeah,
force, okay? So that's why they started on that side and went the other. But there again, we didn't have the input force when we looked at just A either, did we? So you could say, if we, when we get done, well, actually I think we are done, but if we, they kind of, the last line / paragraph of that example says a similar approach results in an internal resisting torque of 800 pounds-inches between pulleys C and D, and zero torque between pulley D and the frictionless end of the bearing. So, in other words, if we did just that, if we cut it, let's see, if we cut it here at S and look back this way, what's going on? Well, if we looked at this, we add those two up, we've got 1,800 pounds-inches trying to go, I can't really see that mouse, trying to go this way, right? Trying to do that. So you would have to have 1,800 resisting back that way, right? That's if we're looking at this same section here. We would have to have 1,800. Well, what did we just figure out we had when we looked at it from the other side? 1,800, right? It makes sense then, doesn't it? It adds up. So 0 equals 0, if you will. Well, then if we cut it at section between C and D, right here, and we only looked at this part, we only have 800 then resisting, don't we? So this shaft can be a little bit smaller. From here to here, that shaft can be smaller. We only have 800 pounds-inches resisting, or that we have to resist. Well, if we cut it right here and looked at the shaft to the right, that's where they're saying we would actually have 0 torque there. Does that mean we can get rid of the shaft? No, not really. Because then we'd have to look at the overall system to see what those two ends would have to work on, right? So, same thing on the other end. If we cut this shaft right here, in essence, that would be 0 as well. There's nothing resisting, there's no external force and no internal force where that bearing's at. So it's just free to spin. So it's kind of a neat, that part of it's really not that hard. You just have to remember that you've got to figure out what the internal force on that shaft is going to be to resist what is being input from the external forces. So once you figure out what the external forces are, then you can say, okay, well then I know what the internal force has to be because it has to keep it in equilibrium.
So the 0, you could use any material for the shaft, basically?
No, I don't think so. Because there's...
Is it actually true that there could be 800 on one side of that pulley D, and then like an inch away it's 0 on the other side of it?
No, and that's kind of what he's saying. Yeah, it's not, in theory, that sounds really good, but no. I mean, in theory, you could just not have anything there, right?
Yeah, so, yeah, I mean, that's what I'm saying, like you could put a string there versus
Yeah.
a piece of steel technically.
No.
No, yeah,
No,
okay.
not going to work.
Yeah.
You would, and what you would typically do is just leave that shaft the same diameter as what you're going to have on the other side of those two pulleys.
Okay.
And that's what you have to have, because you have to be able to get that pulley on there and hold it in. So, yeah, so that wouldn't necessarily fly. Okay? So that's what's going on there. As far as, okay, if I can figure out what kind of forces are acting on those pulleys, then I can go back and figure out what the shaft has to do to overcome that. Well, then you start getting into